Hello there, and welcome back to the series on linear algebra. In this video, we're going to be discussing some relationships between vectors, arguments in 3D, projections, and the concept of orthonormality between vectors. So let's just review a couple of the concepts that we talked about last time. So last time, we introduced the basics associated to vectors, in particular the norm, or the magnitude of a vector, which can be found by doing the sum of the squared components of that vector. So xk, the quantity squared, once you add all of those squared elements up, then you're going to be taking the square root. And also the dot product between two vectors of the same exact dimension can be found by doing the sum from k is equal to 1 to n of the product of their corresponding dimensional entries. Also, we discussed the geometric interpretation of vectors and their relationships to each other. So let's take a two-dimensional perspective. Let's assume we have a vector here, u, and another vector here, v. Keep in mind, vectors are not uniquely represented in terms of their endpoints and base points, so technically v can also be right here as long as that has the same exact angle, and also we have another vector over here, u, as long as that has the same exact length and direction as this red vector, they technically are the same vectors. So if we want to do the vector u plus v, one can show that the sum of these vectors is actually the primary diagonal of this particular parallelogram. So I can actually change this diagram a little bit by rotating these vectors, and I can have an equivalent orientation of these things. For example, let us suppose I have this to be my vector u, and let's assume I have vector v to be somewhere over here. So if I want to sort of create my sum diagonal u plus v, then my v would be over here, and my u would be over here. So which diagonal in this particular parallelogram would correspond to u plus v? So if you look at this diagram on the left, technically we have u, so tail to tip, and if we put the tail of v on the tip of u, then that sort of goes to the direction of u plus v. So if we sort of follow that logic, if that is u, and then we put the base point of v on the terminal point of u, then that would correspond to the location of the sum u plus v. So indeed that is the case. So that means this direction would be u plus v. You can also find it in the similar way doing v plus u using the same exact logic. Now let's actually look at the subtraction between vectors and see if we can come up with a nice interesting property that sort of gives us a nice geometric intuition of what the difference between two vectors represents. So let's look at this particular picture. So let's assume that this is vector u, and let's assume that this is vector v. So if that is vector v and we negate its components in 2 dimensions, the opposite of v would be this vector here. It's going to have the same exact magnitude but a different direction, in particular in 2 dimensions. That would be a 180-degree rotation. So if that is vector negative v, then vector negative v would also be this vector here. So if I do a parallel representation of u, so u would be this vector here, and I were to do, for example, u plus negative v, so u plus negative v, which is the same thing as u minus v, then that is going to give me this vector here. So that is the vector u minus v. Okay, so similarly, you should be able to figure out which is the vector v minus u. So if we follow the same exact logic, so let's draw another diagram. Let's assume that this is u and this is v. Which vector in this particular picture would v minus u be? So if I were to represent this in terms of the old vectors in blue on this left picture, technically u minus v is this red vector, but u minus v also is this vector here. So if I'm only focused on 3 vectors, in particular these 3, so that is u, this is v, and this is u minus v, notice that u minus v is pointing towards u and away from v. So if we use that particular structure and one asks, well, where is v minus u, then that should be towards vector v and away from u. So towards v away from u, so towards v away from u would be that vector there. So this is vector v minus u, and u minus v would have the same exact magnitude just in a different direction. So it would be pointing towards the vector u and away from v. So with those things in mind, what we're actually going to do is develop a formula to calculate the angle in between two vectors u and v. So our goal is to find out what that angle theta is going to be. So let's just draw a very basic picture here. So this is going to be vector u. We're going to drop the dimensions here. So technically this picture could be embedded in, say, 7-dimensional space. So that's a vector u and a vector v, and our goal is to determine what is this angle between them, so theta. So what vector would this vector in red represent? So notice that my direction is pointing towards u and away from v, so that means this vector in red is u minus v. So this picture is similar to just a triangle, right? So if we just draw a triangle with a similar orientation, let's assume this is A, B, and C, and again we're interested in finding this angle theta. These two pictures are very similar to one another, and if you remember from pre-calculus, there's actually a nice little trigonometric law called the law of cosines that represents the length of these triangle sides and the angle between these side segments. So according to the law of cosines, with respect to this latter picture there, we know that c squared is going to be equal to a squared plus b squared minus 2ab times the cosine of angle c, which is the angle in between a and b. So if I were to replace these lengths A, B, and C with these corresponding lengths, because this length A corresponds to the magnitude of u, this side length V and B corresponds to the length of magnitude V, and C corresponds to the magnitude of u minus V, we can get a vector representation for the law of cosines, and hopefully be able to derive an identity for the angle between any two vectors u and v. So once we do that, what will we get? Well, C corresponds to the magnitude of u minus v. You could also do v minus u, and you should be able to see that you get the same exact answer. So that's going to give us the norm of u minus v, the quantity squared, is equal to the norm of u squared plus the norm of v squared minus 2 norm of u, norm of v, times the cosine of the angle between u and v. So let's just explore this term on the left-hand side and see if we can turn it into something that is workable with. So remember that the norm squared of a vector is just the same as the dot product of that vector with itself. So that means the norm of u minus v squared is actually equivalent to doing the dot product of u minus v with u minus v. And one of the properties of dot products is something similar to the distribution law. So this is going to be u dot product u minus u dot product v minus v dot product u plus v dot product v. Notice that these are the same exact things because dot products are commutative, so that's just minus 2u dot v. And remember, again, the dot product of a vector with itself is equivalent to the norm squared of that particular vector. So that means this can be rewritten as just the norm of u squared plus the norm of v squared minus 2 times the dot product of u with v. So that means once we replace the norm of u minus v squared with this expression into this identity, notice that we're going to have the norm of u squared, norm of v squared on both sides of this equation. So once we have that and cancel those things, what are we going to be left with? So we're going to be left with minus 2 u dot product v is equal to minus 2 norm of u, norm of v cosine of theta. Now we have that. That means we can cancel these minus 2's because that's on both of these sides and everything's being multiplied by one another. And then we can solve this equation for cosine of theta by dividing both sides by the norm of u and the norm of v multiplied by one another. So when we do this, we have to mandate that both u and v are not zero vectors because the norm of them would be equal to 0 and dividing by 0 is bad. So if we assume that those things are not violated, we get the beautiful identity that the cosine of the angle between two vectors u and v is equal to the dot product of those vectors divided by the product of their magnitudes u and v, and that gives us a very, very nice result. So let's just do a little numerical example to sort of see how we're going to use this result and sort of what it implies. So a nice little example. Let us assume u is the vector 3, 2, and let's choose another vector v to be the vector negative 2, 5. So what we want is to find the angle between them. So u is some vector over here, and v is some vector over here. So that's v. So our goal is to figure out what the angle between them is. For example, is it 90 degrees, 180 degrees, 20 degrees, 1 degree, or something like that? Negative 15 degrees or something of the sorts. Okay, so the first thing that we need to do is find the norms of each of these vectors and also the dot product between them. So let's start off with the norms because that's relatively easy. So the norm of u is going to be the square root of 3 squared plus 2 squared. So that's going to be the square root of 9 plus 4, so that's going to be the square root of 13. And the norm of v, that's going to be the square root of negative 2 squared plus 5 squared. So that's going to be 4 plus 25, so that's going to be the square root of 29. And let's just do the dot product as well. So the dot product of u and v, that's going to be 3 times minus 2 plus 2 times 5. So that's going to be 10 minus 6. That's going to be equal to 4. Once you have the norms of each of the vectors and the dot product between them, now we can employ this little beautiful formula that we have here. So that means the cosine of the angle between u and v is going to be equal to the dot product divided by the product of their norms. So that's going to be the square root of 13 times the square root of 29. And if you really want to, you can write that as the square root of 377. And once you do that quotient, you're going to have that's approximately equal to 0.2060. Now, with that in mind, you should be able to see that this quotient should be between negative 1 and 1, inclusive of the boundaries, because that is the output of the function cosine. So you should be able to see how to prove that result via a theorem we discussed last time. Okay, so just sort of think about that result for a moment. So if the cosine of theta is equal to 0.2060, what is that angle theta actually equal to each other? So I can take the arc cosine of both sides. So theta is going to be equal to approximately the arc cosine of 0.2060, which is approximately equal to 1.36 radians. Usually we don't like to work with radians, so let's just convert this to degrees. So I want to get rid of radians and I want to convert this to degrees. So there's 180 degrees in pi radians, and that's going to cancel out our radian unit. So once you actually do 1.36 times 180 divided by pi, you can find that that's going to be approximately 78.11 degrees. So that is the angle between these vectors u and v. The next concept that we're going to discuss is the orthogonality between two vectors. So we say that two or more vectors are orthogonal to one another if the angle between them is 90 degrees or pi over 2 radians. So let's look at that angle between two vectors formula and see if we can get any special formulas or corollaries from that particular formula. So remember that the cosine of the angle between two vectors is always equal to the dot product of those vectors divided by the product of their norms. So if theta is equal to 90 degrees, so if u and v are orthogonal, then we have what? So that means the cosine of pi over 2 must be equal to u dot v divided by the norm of u times the norm of v. So what is this going to be equal to? So I don't like fractions personally, so I'm actually just going to multiply both sides of this equation by norm of u times norm of v. So that's going to give me the dot product of u and v is going to be equal to the cosine of pi over 2 times the norm of u times the norm of v. So from pre-calculus, we should know that the cosine of 90 degrees is actually equal to 0. And what is 0 times the norm of u times the norm of v? Well, that should be equal to 0 regardless of the values of the magnitudes of these vectors. But of course, we're assuming that they're not equal to 0, in particular non-zero magnitude vectors. But regardless of what those magnitudes are, the product of the statement should be equal to 0. Therefore, if two vectors are orthogonal, that means their dot product is equal to 0. And you should be able to prove that the converse also holds, assuming that these magnitudes are non-zero. And that gives us a very, very strong theorem that we definitely should be familiar with. So that means if u and v are vectors in the same exact vector space, that means u and v are orthogonal to one another if and only if the dot product between them is equal to 0. And that, of course, can be formally proven very, very simply. Let's look at a numerical example to sort of demonstrate what we mean by orthogonal vectors. So example, so let's assume we let u be equal to the vector -3, 2, and let vector v be equal to the vector 4, 6. And let's do the dot product between them. So the dot product between u and v is going to be equal to the dot product between -3, 2 and 4, 6. So that's going to be equal to -3 times 4 plus 2 times 6, and that's going to be equal to -12 plus 12, and that's going to be equal to 0. So since the dot product between these two vectors is equal to 0, that means u and v are orthogonal to one another. That means if we take a look at the graph between these vectors, so -3, 2 is going to be like this vector here, and 4, 6 is going to be this vector here. If we look at the angle between them, that's actually a right angle. So that means that's what we mean by these vectors are orthogonal to one another. So that's very basic. So what are some of the consequences that we get from that? So let's consider the following picture. And this is going to be a very important picture in a number of applications. So let's assume we have this vector here. Let's assume this is vector v. Let's assume that we have another vector u that is not orthogonal to v. And let's assume that the sunshine, or the sun is right here, and we shine the sun directly on this point such that this projects a 90-degree angle. So there becomes this new vector, which I'm going to highlight in orange, which is a scaled version of v. Right, so remember, scalar multiples of a vector just stretch or shrink that particular vector. So in this particular vector, this is going to be a shrinked version of v where this constant c is going to be less than 1 but greater than 0. So what we want to know is what exactly is this vector CV, and how can we find what this actual number C is? So this orange vector is eventually going to be called the projection of U onto vector V. And let's see if we can figure out what that number C is. So remember, what is this vector in green? So if we actually do a vector here towards U, which vector is that? Well, we should already know that that's towards U but away from vector CV. And we want that CV and U minus CV to be orthogonal to one another because we want that angle between them to be 90 degrees. So with those principles in place, that means we have that CV, the vector, dot product with the vector U minus CV must be equal to 0 because we want that dot product to be equal to 0 to force these vectors to be orthogonal to give us this projection vector. So what we can do is we can distribute CV to each of these things, and notice here that C is a scalar, not a vector. Okay, so that's going to give us what? So that's going to give us C times the dot product of V with U, and then we're going to have minus C squared and then V dot product with the vector V, and again that's equal to 0. So what can we do here? So keep in mind that v times u is the same as u dot v, and I can also factor out a scalar constant c. So that's going to give me u dot v minus c, and v dot v, this must be equal to 0. Let's assume that c is a non-zero constant, so I'm just going to divide both sides by c, and life is good. Right, so here clearly c is not equal to 0. That's an important mandate that we should have. So that means u dot v must be equal to c v dot v, and I can solve this equation for c very, very easily. That means c is equal to u dot v all over v dot v. And remember, the dot product of a vector with itself is precisely equal to the square of its norm. So that means c is actually equal to the dot product of u of v divided by the norm of v squared. So that gives us a nice formula for this constant c, which represents how much we need to scale the vector v down by in order to get the projection of u onto v. Okay, so let's just summarize these concepts that we've built at this point. So here's vector v, here's vector u, here's some orthogonal projection here. Again, this is u minus v, and then we have some new vector, our new character. I'm going to put that in u. So this is the projection, so proj, the projection of u onto v. So v is going to be a subscript here. So that's going to be a scaled version of v, and what's that scaling factor? That's going to be this number here. So it's going to be u dot v divided by the norm of v squared times v, the vector we are scaling down. So in this particular picture, we have that c is less than 1. Okay, so how do we read this expression? So this is the projection of u onto v. All right, and when we say this, also note, in order to keep your terminology and geometric understanding straight, the right angle is with respect to v. Okay, notice the right angle is on vector v, not vector u. That would be the projection of v onto u. All right, so notice in this picture, so in this diagram, notice that the c is less than 1. If you were to make it longer in order to generate that projection, for example, if my vector v was right there, that means I would have to make it longer in order to obtain my projection. All right, so let's just do a little numerical example just to illustrate how to calculate a particular projection vector. All right, so let's assume we let u be the vector -3, 2, and let's assume v is the vector 4, 7. So let's calculate the projection. Let's do v onto u. So that's going to be equal to, via the formula we derived, that's going to be the dot product of v with u divided by the norm of u squared times u, because that's the vector we are scaling in this particular picture. So what is the dot product of v with u? And that's of course the same as the dot product of u with v, but let's just do it in that order to keep our minds in the same exact direction. So that's going to be -3 times 4, so that's going to be -12 plus 2 times 7, that's going to be equal to 14, divided by the norm of u squared. So that's going to be the norm of u. So that's going to be 9 plus 4. And we're going to be scaling the vector u, which is the vector 3, 2. So keep in mind that this is a scalar. This is a vector. So the projection is a vector. So that's going to come out to what? So 14 minus 12, that's going to be equal to 2, and 9 plus 4, that's going to be equal to, what is 9 plus 4? That's going to be equal to 13, and that's going to be multiplied by the vector -3, 2. And then we can distribute this scalar into this vector to each of the components, and that means this is going to be equal to -6 over 13 and 4 over 13, and that is going to be the projection of v onto u. Now, of course, this formula for projections might seem like it's overcomplicating things, and you may be like, okay, well, what if I don't want to calculate shadows and things like that? Well, there's actually several different applications that result from projections, so let's just take a quick detour and look at a sneak peek at one of the important applications that we're going to take advantage of later on in this series. Before we get into that application, let us briefly look at a particular perspective of this projection calculation. So let's again consider two vectors. I'm going to call them u1 and u2 instead of u and v, because eventually we want to construct a set of n vectors that are going to have some special property. So let's just start with 2, and later we'll get into the generalization of this particular structure. So the projection let's do u2 onto vector u1. This is going to be equal to what? So that's the dot product of u2 with u1 divided by the norm of u1 squared times the vector u1. So what I want to do is I want to decompose this square into something times something, in particular norm of u1 times norm of u1, and then I'm going to rearrange this. So this is going to be equal to u1, and you can do dot product with u2 because they're commutative. I'm going to do u1 over the norm of u1, and then I'm going to dot product that with u2, and then I'm going to multiply that by the vector u1 all over the norm of u1. And you may want to take a moment to sort of think about why this is true. And now take a moment and pause the video if you want to and sort of think about what's so useful about looking at things in this way. So notice I'm taking a vector u1 and I'm dividing it by its norm. What type of vector do you think that's actually going to generate? So you should notice if you take a vector and divide it by its norm, you will always get unit vectors. So u1 over the norm of u1 are both vectors of size 1. So let's actually give that a special name. So I'm going to call q1 to be equal to u1 divided by the norm of u1. So some people will refer to this as the normalized or unit vector form of u1. So once I write it like that, that means I can give this formula a nicer structure. That means the projection of u2 onto u1 is actually just equal to q1 dot product with u2 times q1. And doesn't that formula look so much better? Maybe, maybe not. It's up to you to decide that. All right, so what are we going to actually do with this special formula, and what is one of the special applications for it? Well, it comes from this particular theorem, and then we'll look at the consequences of it. So what I'm going to do is I'm going to define a new vector. I'm going to call it u2 star, and I'm going to call this vector u2 minus q1 dot product with u2 times q1. So this is just a new vector. So there's a vector. Remember, this is a scalar because the dot product of two vectors is a scalar, and then that's a vector, right? So we have a vector minus a vector, so that's going to give us a new vector. We're going to be calling that u2 star. So what is so special about this u2 star vector? Then u2 star dot product with this original normalized vector q1, this is actually always equal to 0 regardless of what u2 actually is. So u2 could literally be any vector in the world in this particular vector space. And this transformed version of u2, which we call u2 star, is always orthogonal to q1. Which means it's also orthogonal to u1, but we like unit vectors because they're very pretty. So let's see if we can actually prove that these two vectors, u2 star and q1, are actually always orthogonal to one another, and then we'll look at why we care about it. So what is u2 star dot product q1 equal to based on the definition that we have? So u2 star is defined to be equal to this structure. So u2 minus q1 dot product u2 times q1, and we're doing the dot product of this vector with q1. And let's actually do a distribution of q1 with that vector and q1 with that vector. So that's going to be equal to u2 dot product with q1 minus q1 dot product with u2, q1 dot product with q1. All right. So now that we've distributed, what can we do here? So notice that we have something special that we can factor out. In particular, I'm going to rearrange this using the commutative property to make it a little bit more obvious, because q1.u2 is the same as u2.q1. So this is the same as u2.q1. I'm going to put that in parentheses, minus u2.q1, and then we're going to have q1.q1, and you should know what that is equal to, right? So I'm going to factor u2.q1 out of these terms. So I'm going to have u2.q1 times 1 minus q1.q1. So when you take the dot product of a vector with itself, what is that equivalent to? Well, we should know that that's the same as the norm of that vector squared. So we have 1 minus the norm of q1 squared. Now, what is so special about the vector q1? That is a normalized version of the other vector, right? So if that is a unit vector, that means the norm of q1 is 1, right? So that means this is going to be equal to u2 dot product q1 times 1 minus 1. That is 0 for any u2 and q1, in particular u2, right? So what have we shown? We have shown that u2 star dot product q1 is equal to 0 regardless of u2. And now you may see why we want that special little property, that vector u1 is actually normalized. So that is very, very interesting. So what exactly have we done here, and what is so special about this little formula and trick? So what we've done is we've made it possible to construct a set of orthonormal unit vectors. Technically, I don't need to put unit vectors there because that's part of the normal thing. So it's a set of orthonormal vectors. And when I say orthonormal, I mean orthogonal and unit vectors, right? So using this process, and eventually we're going to call this the Gram-Schmidt process, allows us to create an orthonormal set of vectors for any set of vectors. Now let's look at an example to sort of illustrate how we're going to go about that. Actually, let's just summarize that, and we'll save the complicated examples for actually when we do the Gram-Schmidt process. At least just be aware of its construction and how to prove that it can work. So if u1 and u2 is a set of non-collinear vectors, and when I say non-collinear, I mean that they are not in the same exact direction, with q1 equal to u1 divided by the norm of u1, and u2 star to be equal to u2 minus q1 dot u2 dot q1, and let's define q2 to be equal to u2 star divided by the norm of u2 star. Then, what is so special about the set q1, q2? q1, q2 is a set, or always a set, of orthonormal vectors. For now, this is just a theoretical consequence. We'll focus on the actual implementation. We'll also do it in a programming language also, because this can definitely be a little bit tedious. And we'll wait until we actually do the generalized versions, for example, 3 vectors, 4 vectors, or possibly 50 vectors, and then see what its consequence may be. So without further ado, let's actually do another important relation between vectors, in particular the arguments of vectors, and dimensions higher than 2 dimensions, since at this point we've actually only talked about arguments in 2D. Now that we've developed a formula that allows us to calculate the angle in between any 2 vectors regardless of the dimensions that we're in, we can actually use this in order to generate a nice little way of calculating the arguments of vectors in 3 or more dimensions. So let's go ahead and see if we can construct such a procedure. So consider an n-dimensional vector space with I1, I2, down to In special 0, 1 vectors. For example, I1, this is the vector 1, 0, 0 down to 0. This is the vector 0, 1, 0 down to 0. and all the way down to, this gives us the vector 0, 0, 0 down to 1, where 1 is the nth position. Right? These special little unit vectors, right? So what we want to do is we will actually want to represent the angle between a vector u and the principal axes of that particular dimension that you're interested in. So what we're going to do is we're actually going to represent that as the argument of that particular direction. So we're going to do argument k, so k could be x, y, z, or dimensions 1, 2, and 3. Let's actually call this theta k, just to keep things short. So via that little angle between vectors formula, that means we have that the cosine of theta k is actually just going to be equal to the dot product of u with vector ik divided by the norm of u times the norm of ik. Now remember, regardless of which vector you're looking at here, I1, I2, I17, In, they are all unit vectors. That means this norm is always equal to 1. That means this cosine representation can be represented as the cosine of theta k is actually just equal to u dot I hat k divided by the norm of u only. That's a very nice little formula as well. Okay, so let's actually look at the two-dimensional case and see if this formula actually makes sense to us. So let's look at it, our two-dimensional case. So here's our x-axis, here's our y-axis. Let's draw our little unit vectors. So this is going to be I1, this is going to be the vector 1, 0, and this is going to be our other unit vector. This is going to be I2, this is going to be 0, 1. All right, so let's assume that we want to find the angle of this particular vector u, where u is actually equal to the vector 3, 2. Now let's assume that we want to find this angle theta, and let's call it theta 1, because it's the angle with respect to principal axis 1, which is just theta in the two-dimensional case. So using this little formula that we've built, we actually have that theta 1 is going to be equal to the arc cosine of the dot product of that vector 3, 2 with the vector for which we want to find the angle between it and the vector we have. So that's going to be equal to 1, 0 divided by the norm of our vector u, which is going to be equal to the square root of 9 plus 4. All right, so once you actually do that, we're going to have what? So theta 1 is going to be equal to the arc cosine of, so that's going to be 3 times 1, which is 3, plus 2 times 0, which is 0. This is going to be equal to 3, divided by the square root of 13, and that's going to be equal to approximately 0.5880 radians, which is actually equal to 33.69 degrees. Now, is this the same exact answer as the other formula that we have? So the other formula that we had said that theta 1 should be equal to the arc tangent of the vertical component, which is going to be 2, divided by 3, and actually you should see that that is also equal to 33.69 degrees. And isn't that interesting? So if you have some rigorous understanding of trigonometry, you should be able to prove why these two formulas actually give you the same exact answer. So that's pretty interesting to explore. Now that we have some general understanding of how we can find the direction of vectors in multiple dimensions, let's actually shift up to 3 dimensions and see how we can sort of go about defining a vector in terms of its magnitude in 2 directions or just 3 directions overall. All right, so let's consider a vector in 3 dimensions. Let's assume u is equal to -3, 2, and 1. So the very first thing you need to do in order to calculate directions in multiple dimensions is calculate the magnitude of this particular vector. So the norm of u is going to be equal to 9 plus 4 plus 1, so that's going to come out to the square root of 14. So what is the x angle? So that's going to be equal to the arc cosine of -3 divided by the square root of 14. So where is this -3 coming from? So -3 is coming from -3, 2, 1 dot product with the x identity vector. So that's going to be 1, 0, 0. That's going to be equal to 3. So how would you find theta y? So that's going to be equal to the arc cosine of 2 divided by the square root of 14. And again, where is this 2 coming from? So that 2 coming from is coming from negative 3, 2, 1, dot product with 0, 1, 0, which kills off all of the values except for that second row term. And you can find that that one is going to be approximately equal to 143.30 degrees. That's going to be approximately equal to 57.69 degrees. And how would we find theta z if we really wanted it? So that's going to be the arc cosine of the third component, which is 1 divided by the norm of the vector, and that's going to come out to approximately 74.50 degrees. So keep in mind, if you want to represent a vector u with respect to its angles and or magnitude, since we're working in 3 dimensions, you can either give these 3 dimensions, and that defines the vector, or you can represent this vector in other coordinate systems with respect to its magnitude and any 2 of its angles, or you can represent them with respect to all 3 of the angles, theta, x, y, and z. As long as you have 3 pieces of information to represent this 3-dimensional vector, then all is going to be well. But this is how you calculate the directions of vectors in 3 or more dimensions. Anyway, those are more of the basics associated to vectors and their relationships with other vectors. In the next video, we're going to go and introduce the concept of matrices and some of the properties associated to them. Hope to see you there. Take care.